All right. So we have been working towards analyzing systems that have potentially multiple objects in them. We've talked about kind of rigid objects where we can define a system as having multiple objects within it, and as long as there's no relative motion, we can look at just the stuff that's going on or the forces coming on from outside the system. And we want to ultimately work towards a purely dynamical system where I can have a system of multiple objects. The stuff in that system might be moving relative to each other, and there might be things, impacting the system externally as well. I could think in the vast limit of going down to the idea of continuous systems, where the individual objects might be individual protons and neutrons and electrons. So I can think of the system having a wealth of individual little tiny objects that might be well represented mathematically as a continuum. There's a bug flying in front of this camera. So let's try to motivate some of the mathematics behind dealing with continuous systems, but we'll mostly stick with static situations right now and save dynamics for later. And I think the way to introduce this idea is to think about now not massless ropes, but let's let the rope have some non-zero mass. But I'm going to motivate it by doing examples that have massless ropes. And you'll see how these examples are ultimately going to tend towards us being able to analyze a case where the ropes themselves have some mass. So let's suppose you have a rope that's holding onto a box, a single box in this case of mass big M. The rope has length capital L. And I could ask, in this case, there's one massless rope. I'm going to call it T sub 1. What is the tension in this rope? And I'm going to, in this coordinate system, define up as positive and define the location of the bottom box as 0 so that the roof then is y equals L. Well, this is pretty trivial and everything's going to be statically just hanging there. This is pretty straightforward. There's a force pulling up on the box. There's gravity pulling down on the box. Everything is static. So that suggests that the tension in this rope is the full mass, which in this case is just one box big M times little g. And the length of the rope, or the length of what will ultimately be the distance between boxes, or the length of this rope, is just capital L. All right. Hopefully that was not too profound. Now let's take the same system and break that mass up into two equal mass boxes that are now separated by each other. So this thing has mass M2, this bottom box also has mass M2. And now kind of the length of a piece of rope in one of the boxes is then L over 2 instead of just L. So there are there's box plus rope and then box plus rope. And the overall length is still big L. And as you can see, the total mass is overall still big M. But now there are two ropes. So there's a tension 1, and now there's a tension 2 that we have to think about. What are the tensions in those ropes? Well, again, not too bad. The bottom box, what's touching the box? T1 is pulling up, and then there's gravity pulling down, and everything is static. So it looks like T1 is then just M over 2 times G. And then for the top box, what's touching the box? T2 is pulling up, T1 is pulling down, and then gravity is also pulling down. And that better be equal to 0. So it looks like then T2 is big M times G. Or, in this case, you see that the tensions are different. The top rope has to hold up both boxes in a sense, where the bottom rope only has to hold up one box. And to motivate the way I'll write this in a bit, I'm going to write this now as instead of M times G, since each box is M over 2, I'm going to write that as a multiple of the mass of the individual box. In this case, individual box is M over 2, so it's 2 times the mass of one of the boxes times G. The bottom rope is 1 times the mass of one of the boxes times G. With the length of the ropes in between boxes is now L over 2. And I could ask how the tension has changed in going from one rope to the next rope. So in this case, I could say T2 minus T1. What is the change in the tension as I go up the rope? Well, that looks like then it's just m over 2 times g as a result. Every time I step up to the next rope, it looks like, in this case there's only 2 ropes, so I can't do that plural. But every time when I step up to the next rope, the tension increases by a additive m over 2 times g. The tension increases as you go up the rope. Okay, let's do this again. But now let's have there be 4 boxes, each with mass m, capital M divided by 4. Distance is still overall length L. So the length of a rope plus one of the boxes, little l, is then L over 4 in that case. And it looks like then there are 4 pieces of rope. This bottom one here is T1, T2, this one here is T3, T4, then this thing is T2. What is the tension in each of those 4 pieces of rope? I'll just skip to the answer. So then I could write the tension of T1 is going to be m over 4 times g. T2 is going to be 2 times m over 4 times g. T3, 3 times m over 4 times g. T4, m times g, or 4 times m over 4 times g. So I'll say in general in this case, for t sub n, where n is 1, 2, 3, or 4, it is little n times big M over 4 times g. Along with the length of each individual piece of string is L divided by 4. And I could ask, how does the tension change as I go from rope to rope? Well, you can look at the difference of 2 successive pieces of string, T2 minus T1, or T4 minus T3, or T3 minus T2. And you'll notice that it is m, in this case, m divided by 4 times g. Every time you bump up a little piece of rope, the tension is increasing as you go up. But all the while, the length of each piece of rope is shrinking to smaller and smaller distances, and the mass of each box is also shrinking. So where in the top case, all the mass was concentrated as a bob at the bottom. But then as we've gone from 2 to 4, the mass becomes then more uniformly spread out across the entire length L. So you can probably see where we're going with this. Go now to capital N boxes. And we've established a pattern, so I can just write down the answers without figuring this out. So in this case, each box has mass, in this case, big M divided by big N. Each box now has whatever mass that is. The lengths of rope L becomes big L divided by N in that case. As well as I can say that the tension in string N, where again N is 1, 2, 3, all the way up to capital N, is then going to be little n big M over big N times G. And as that little n gets bigger, you're getting higher and higher up the rope. Again, with now this delta T, the tension in between 2 successive pieces of rope, right? T sub 49 minus T sub 48, or T sub 1003 minus T sub 1002. Looks like it's M over big N times G in this case. The tension is arising in the string. Notice here, if you think of now we're getting to N being very, very big, as you slowly but surely step your way up the rope, the tension is slowly but surely increasing as little n gets bigger and bigger and bigger. So the tension is occurring in the rope, or in this case, just the distribution of boxes, or rather it's occurring because of the distribution of boxes. The tension is arising because of the distribution overall of mass. as we let big N get bigger and bigger and bigger, you can think of the mass as being kind of stretched more and more out, more uniformly along this rope. Did I bring a rope? Oh, I actually have a rope this time. Where instead of it thinking of this like a rope, you can think of it as a bunch of tiny, tiny, tiny little boxes attached by massless little strings in between them. We're modeling, in this case, a rope that has some actual non-zero mass as just a bunch of tiny little bits of mass attached by massless strings. And so we'll call that rope that has massful, or non-massless rope, or rope that has mass. So now let's go to the calculus limit. Now let's let n go to infinity. We have to think of this now in a calculus sense. What in the above pattern of expressions that we've created can we replace with calculus notation, like differentials or derivatives? Well, again, the tension, we're ultimately seeking the tension here. The tension is arising because of a distribution of mass. It's how the mass is spread out. So mass is kind of the independent variable here. So as n goes to infinity, in this case, if I look at big M over big N, that's getting smaller and smaller and smaller because I've never changed big M in any of these cases. I'm just spreading it out over the rope. So this is going to what I might call dm. It's becoming, as n gets 10 to the 9, 10 to the 20, this m divided by big N is becoming incredibly small as I kind of refine the size of the boxes that are being spread out. So you can think of this as a small increment of mass. Right, small changes in the mass as you move up the rope. Such as you go farther and farther up the rope, you're adding up more and more of these things that ultimately, when you go from the bottom to the top, should be the total mass, of course. If that's the case, then delta t above looks like it was written as m over big N times g. That goes to dm times g. And so to make the notation correct, since we're talking about things, we're thinking of these things in the calculus limit, again, where dm is exceptionally small but non-zero, but dm squared is so small we can ignore it. Where delta t or delta m might be some big bulk change. So what I really want to write this as is that now that delta t becomes dt times dm, or is equal to dm times g. The changes in the tension have gotten so small. We'll let that go to become dt. A small change in the tension as you go up the rope. As you go up the rope as well, a small amount of mass is added to the system, or added to the rope if you think of the total mass as you go up the rope. Similarly, little l, kind of the distance between the boxes, was L over big N. So that then is going to become, that L over big N is going to become smaller and smaller and smaller and smaller. So instead, let's write this as, I could say dl. Maybe I'll just write it as dl then in this case. Or, okay, let me write it as this. I could say that L kind of becomes then dl in this sense, because little l is becoming so incredibly small. Why use L? I could also, since we're dealing with all of this as happening vertically, right, I could call that dy in this sense too, right? Because in my coordinate system, I've aligned the rope with the y-axis as n goes to infinity. So in this case, also notice that if I write dt, which I originally is m divided by n times little g, and then do I still have it on the screen? Yeah, I still have it up here. I then also have little l is big L over n. I could essentially solve this for n and then plug that into this expression. So if I do that, then delta t is not m over n times g, but m times g, and then there's the n is going to be big L divided by little l. So then this becomes m times g times little l divided by big L. Big M's a constant, g is a constant, big L's a constant. Little l is changing, namely as n gets bigger and bigger and bigger, that distance shrinks. Similarly, how we said delta t, as n gets bigger and bigger, shrinks, and we eventually call it dt. So let's now do that. This also says that dt, if I let n go to infinity, well, there's a bunch of constants, and then this L, then I'm going to write as dl, or I'm going to stay with dy in this case. Particularly, I'm going to write this as m divided by big L times g times dy. Because I want to draw attention now to that thing in parentheses. I'll even highlight it. This thing in parentheses here. The total mass of the rope divided by the total length of the rope. That might sound like a density. That's because it is. Mass over length for a 1D density, this m over L is the 1D density for the rope, namely the uniform rope. A uniform rope, implying that I take the entire mass of the rope and I uniformly spread it out in a bunch of infinitesimally small little boxes of mass m, with no one location of the rope having a clump of more boxes compared to the other. So this is, in this case, the uniform 1D density, the amount of mass over the 1D length in this case, as opposed to, say, a volumetric density, where it's the total mass divided by a volume, how it's spread out over a 3D surface. So I might call this, give it a symbol, and call it sigma, in this case, for the 1D density. So in this case, this sigma is playing the role of m over L. Something as units of mass divided by length for a 1D system, like a rope. So in that case, this bottom expression then says that dt equals, I had m over L times g times dy. I'm going to write that as sigma times g times dy for that second expression. But above, which I think I've lost, where I've lost it. Oh no, I didn't lose it. Now note, if I look at this expression, here's one expression I have for dt, and then here's another expression I have for dt. So this also implies that sigma g dy, which equals dt, is also the same thing as g times dm. Two ways I arrived at the same expression for how the tension changes as I go up a tiny little piece of rope. So then this implies what? This implies it looks like sigma, the g's on both sides cancel, dy equals dm, or it says that sigma is dm divided by dy. And this I'm going to put a box around and also highlight. Because the sigma we've defined as density, the 1D density, and then I've come up with an expression in the calculus limit that's defining it to be dm divided by dy. Sometimes people start with this and just say, like, here's how we're going to define density. In this case of the example of uniform mass distribution, it was easy enough to derive this without kind of imposing it as a definition. But in general, this is the definition of 1D density. If I tell you the 1D mass density of a system, I'm telling you what the function or value is for the derivative dm by dy, how the mass changes over a small change in length. Again, remember, we always should be able to convert these calculus mathematical notations statements into stories. Right, I should have even wrote this in a different color to emphasize that this is something worth remembering. The 1D density, the definition is dm over dy. And just as an aside, we won't need this for a bit. But for example, if I wanted to find a 3D density, maybe I'll use, rho in that case. Rho would then be defined to be dm over a volume. So it might be something like dy cubed, something. Well, if I use Cartesian coordinates, it might be divided by dx, dy, dz, or something like that. Would be the definition of a 3D density. 2D density, mass over area, dm over dx times dy, or something like that. So with this definition, and this, by the way, the sigma, the definition of sigma being dm over dy, since this is general, this general statement, that sigma need not be a constant like it was for the example we're doing. In the case where the example we're doing, for uniform, then sigma, in this case we saw, was just the total mass divided by the total length. It need not always be that way. Sigma could itself be a function of y, or a function of volume, or whatever. You could have a rope that gets thicker as you go up. Maybe we'll do that one after this. Or as you go up the rope and it gets thicker, right, the density of how much rope, how much mass changes. So when you have more general systems, you can always start with the definition dm by dy is sigma, whatever that is. That gives you a way of evaluating mass, because you could then figure out what dm is and then integrate. And in cases like this tension, it might help you solve more general problems. So in this case, let's see, I guess we haven't solved the full problem for the tension in this uniform rope. Actually, let me just do what I just said. So we're still sticking with the uniform rope that's hanging. That's length big L, mass total M, but has a uniform density. So we know that sigma in this case is just big M over L, which is a constant. But that by definition is little dm over little dy, since everything is hanging vertically. What is the total mass of the rope? Well, in this case, again, since we kind of worked backwards, it better be capital M. But just to demonstrate how you do this in practice, right? If sigma equals dm over dy, then that implies that dm equals sigma times dy. Since sigma is a constant, we have separated this very simple differential equation, which only has a first derivative. So then I could integrate both sides. And I know if I'm doing the total mass of the system, again, I'm thinking my coordinate system, I'm going from the bottom where y equals 0 to the top of the rope where it is at height L off the ground. And then that corresponds to when I'm at the bottom of the rope, I've summed up no rope. But then once I get to the top of the rope, I've summed up the entire rope. So that better be capital M. The left integral is pretty easy, it's just M. Since sigma is a constant, that just equals sigma times L. And indeed, we get another derivation of what we said before, where in this case, sigma is just M over L. Or that the total mass of the rope is whatever the mass density is times the total length, in the case of a uniform rope. Again, we kind of did this backwards. We'll do another problem after. But then I can also ask about the tension in the rope. Let me pull this part here to the next page. Oops, not zoom. Simple enough, I could have just rewritten it, but oh well. Right, so in this case, I have, again, a hanging rope, and I've written it as sigma times g times dy, where sigma is just a constant. Note that this says, if I wanted to think of this like a derivative, that dt by dy is sigma times g. how does the tension change as you go up the rope, right? A change in T after a little change in Y, that's the left-hand side. It is increasing, because it's a positive number, by sigma times G. Every little dy you step up, the tension increases by some amount proportional to sigma times G. But I'm going to keep it as it originally was written. dt is then sigma G times dy, which, since it's uniform in mass, I could write this as m divided by big L, G times dy. And now I have a separable differential equation. The left-hand side only depends on T. The right-hand side only depends on Y, since M, G, and big L are constants. So again, I could ask, what is the tension at some arbitrary position Y up the rope? So if I redraw it real quick, here's the rope. If I go up to some position Y, where the top is L and the bottom is 0, what is the tension in that part of the rope? And we should be able to check with the answer we get at the end of the day that when we plug in Y equals 0, we better get 0. When we plug in Y equals capital L, we better get big M times G. It better match the pattern we had when we were looking at discrete boxes. Well, for the Y integral, it looks like I'm going from 0 to Y, some arbitrary location, Y in this case, starting from the bottom. So then to make my limits match, I'm starting at the bottom where I know the tension is 0. And then I'm going up to some arbitrary location. So what is the tension at that location, Y? Again, left-hand side is pretty easy. Then it just says T at Y minus 0 equals, and this is just a constant, times Y in this case. So it looks like the tension at some point Y, which I can plug in a continuum, is big M times G over little y over big L times Y. And indeed, when I plug in Y equals 0, I get 0. When I plug in Y equals capital L, I get the full M times G, as must be the case. So this is the case where we have done it for a continuum, a continuous rope. But we kind of worked backwards in that case. Let's do one where if you wanted to start immediately with the continuum, how you might do that. So let's take the case where, again, it's between 0 and L, and this rope has total mass M, again. But notice how I've drawn it. It looks like the rope's getting thicker as you go up. So, but sigma in this case is a function of Y, which it's going to say be sigma naught times Y itself. So the density is 0 at the very bottom, and then the density, or you can think of this, if you need something more easier to visualize, you can think of the thickness of the rope perhaps is getting thicker, and there's more mass kind of concentrated in the rope as you get higher and higher and higher. Then I want to ask, what is sigma naught in terms of capital M and capital L? And then again, what is T at some arbitrary location Y? What is the tension in the rope at some point Y as you go up the rope? Well, towards the first question, again, this says that sigma naught times Y equals, by definition, dm by dy. Sigma naught's a constant. You can think of what units it better have. Better had units of mass divided by length squared, so that the whole thing on the left-hand side is mass per length, which is the definition of density. So then this suggests that dm is sigma times y times dy. And again, we can integrate. If I want to relate this to the total mass in the system, right, I'm starting at the bottom, I'm going all the way up. In that case, I'm starting where I've added up no mass, and I'm adding up, and I'm getting to the total mass of the rope at the top. So this suggests that big M equals, this is also how you could find, if you didn't know the total mass of the rope, but knew sigma naught in this case, right? This also would tell you the total mass of the rope. So then this looks like it's sigma times L squared divided by 2. Or that 2 times M over L squared equals sigma naught. Indeed, it seems like it has units of mass per length squared, as it must in this case. So that the units work out. Again, units do not lie. What about now the tension in the rope as a function of y, as a function of height? And again, we can come up with some points that should make sense so that we can check our answer. And again, if I have a rope, if I think of the rope at the very, very bottom, I anticipate the tension better go to 0 at the very, very bottom. Right? That tiny little piece of rope at the very, very bottom essentially has to hold nothing else up. So the tension better go to 0 at the bottom. Similarly, at the very top, well, since this is a solid system, solid or static system rather, I can think of it like we did in the previous modules of, let me treat this entire thing as just one object. Well, in that case, that total mass is M, with G pulling down on the thing. So the tension probably should be something like M times G. Essentially, the tension at the very top of the rope has to be holding up the entire mass underneath it, which is just the total mass big M. So it better be something like M times G at top. Let's see if that's borne out. Let me redraw. Here's the rope. And now let's think of, I want to find a differential equation that allows me to then solve to get tension as a function of y. So let me just pick an arbitrary little point. Actually, that looks like I picked the middle. Let me pick an arbitrary point on the rope, a tiny little piece of mass, and I'm going to do a force analysis on that tiny little piece of mass, which I'll redraw here as this little dm. That's some height y off the ground. Well, this little dm, if I do a force analysis, there's going to be a tension on that from the rope above, right, just above that little dm, whatever that tension is. Then below it, there's going to be the tension from the part of the rope immediately below. And I might think of this as the part that's immediately below as the tension at the height y, where then right above it might be T at y plus dy, right? I go up a tiny little bit from the bottom of this little dm to the top of the dm. And then I also have gravity pulling down with what force? Well, in this case, dm times g. It's small because I'm looking at a tiny little piece of mass, but nonetheless, gravity is pulling down on that little red dot that I've signified. So then it looks like I have something like the tension on the upper rope minus the tension on the lower rope minus dm times g. Since everything is static, that better equal 0 in this case. And depending on how mathematically sophisticated you want to be at this point, you can think of what is that difference on the left-hand side. It's the difference of two tensions that are exceptionally close to one another. So I expect that tension, that difference of tensions, to be very, very small. Go back to the previous problem, and we saw that the delta t got smaller and smaller and smaller. We eventually called it delta dt. So now it looks like I have dt minus g dm equals 0 as a result. The more mathematically rigorous way to think about this is you could not make that approximation, but do a Taylor series expansion of d or t rather, at y plus dy. Expand that out, centered at t at y. You'll get that the t at y's cancel, and you're left with a derivative expression, which ultimately is what I wrote down. Now the next step here, well, for one, I guess this tells you could solve for dt as a function of m, and it looks like that's just equal to g. But then you got to think about what this means. How does the tension change, the numerator, as you add more mass? That's the denominator for that derivative. How does the tension change as more mass is added? That is equal to little g. The more and more little dm's you throw in, the more the tension increases by proportional to g. I'd rather, if I could, get this as a function of y instead and do this as a function of position rather than as a function of m. I could, of course, write t as a function of m, where little m could go from 0 to capital M. And that does correspond to unique positions of the rope in this case. But how could I instead write this as a function of y? Right, dt equals g dm. But now I need to bring in that I said before that dm dy is equal to sigma naught times y, which then implies that dm is sigma naught y dy. This essentially is the same thing you would do when you do, say, a u substitution for an integral. Right? You say, if you're integrating over x, then you say u equals some function of x, then you get du equals something times dx, and then you swap things out. That's essentially what you're doing here, right? I'm creating a conversion between y and m, but using something that's physical, right? I'm using this density function to change my units in this case. It's not just some mathematical trick. So using that, then this looks like it's g times sigma naught times y times dy. Well, that's great, because now I have the left-hand side as a function of tension, and then the right-hand side is a function only of y with some constants. Actually, I'll just recopy it. And then ultimately, I can integrate. I want to go up to some arbitrary location. So I'll just write this as I'm starting from the bottom 0 and going up to y. Then I get asked, then the limits have to match. So then the tension at the bottom of the rope, we argued, is 0. And then it goes up to whatever the tension is at some arbitrary location. Did I always have to start at the bottom? No, I could have started at the top in both cases and went down to some arbitrary location. As long as you're careful with what the limits are, you'll always, of course, get the right answer. Same answer, rather. All right, if I integrate this gets t as a function of y minus 0, and then this is equal to sigma g y squared over 2. Or that the tension as a function of y is sigma g L squared over 2. Oh, sorry, y over 2. Y squared, rather, over 2. Indeed, it starts at 0 and gets bigger and bigger and bigger. We took the time to already figure out what sigma naught was. We said it was 2m over L squared up here. So I could come back down here and substitute that in. So I could write in 2m over L squared for sigma, then there's a g, a 2, and a y squared. So notice the 2's cancel, and this looks like it's big M times g, and then I could bring the y, or I could bring the little y and the big L together and say that it's the quantity y divided by L squared at some arbitrary location y. But notice that then if I plug in big L, which corresponds to the tension at the top of this big rope, it is just big M times g as a result. as was expected. In the cases where you can figure out the exact value at a particular location, you can always use those as sanity checks when you try to do it something more arbitrary or continuously, like in this case. All right, I was going to do another example of spinning a rope in a circle, but I think since we're at the 40-minute mark, I think these are good places to start. So again, the approach of you have the mass kind of more, when you have the mass more continuously spread out, focus on pick a little bit dm, and then call that your system and do your analysis on that system. In the cases of ropes and whatnot, or surface tensions with surfaces or plates, or volumetric stresses or something, where you can think about the forces that are acting on that little dot of mass from all sides that you're considering, and you can approximate those. Likely the differences between one side and the other is going to be very small, so you can approximate the difference of those two forces, real forces, as a dt in this case, or a d surface stress or something like that. All right, sounds good.